Looking eastward from the control tower at Wright Field on May 18, 1942, an astonished operator gave the green light for the landing of the XR-4. As this unconventional craft settled quietly to a spot on the ramp, the historian of the first successful American helicopter had descended from the realm of aeronautical speculation to a very material place on the flight line of the Army Air Forces. This event marked the successful termination of the first cross-country flight and delivery of a practical Army helicopter. Made by the Sikorsky Aircraft Division of the United Aircraft Corporation at Bridgeport, Connecticut, the XR-4 was flown 761 airline miles to Wright Field, Ohio, where for 8 months it underwent experimental flight tests. During this entire period, only minor mechanical bugs were uncovered in its mechanism, a record unique in the history of new type aircraft. The helicopter is capable of aeronautical maneuvers unattainable in any other type of airplane. It can hover stationary in space indefinitely under perfect control, resembling the flight of birds more closely than anything previously designed by man. It can fly forward, backward, sideways, or turn on its own axis with equal ease. It can rise vertically from a stationary position on the ground and can be safely landed on a level area 20 feet square. Its designer, Igor Sikorsky, began his world-famous career in 1908 with an unsuccessful attempt at constructing a helicopter. After 30 years of intermittent speculations on the direct lift principle, his plans for a practical helicopter of his own design were carried to a successful conclusion. On the 6th of May, 1941, he was able to pilot this skinless predecessor of the XR-4 to a world's endurance record for this type of craft. He remained aloft for 1 hour, 32 minutes, and 26 seconds. While most of his reputation has been realized in 4-engine ships of the fixed-wing type, the helicopter principle has never been far from Mr. Sikorsky's mind. The story of the helicopter is 4 centuries old. Our earliest existing record of the conception of its principle is to be found in the notebooks of Leonardo da Vinci. This simple sketch is so lacking in detail that it may leave one in doubt as to his purpose, but the accompanying notes are convincing. He writes, "I say that this instrument, made with a helix, if well made, that is to say of flaxen linen, of which one has closed the pores with starch, and is turned with great speed, the said helix is able to make a screw in the air and climb high." There is no evidence of Da Vinci ever having made a model of his machine, but there have been others. In 1922, the Army Air Forces evidenced their first active interest in helicopter development by sponsoring the Russian-born engineer de Beaufezat, who built and tested this huge craft at McCook Field, Ohio. During the captive flight stage of its development, we find its progress being observed by General William Mitchell, then Assistant Chief of the Air Forces. De Beaufezat apparently had no time for scale models. His craft weighed 3,600 pounds and was powered by a 220 horsepower engine. His best efforts never got it beyond the reach of a 6-foot man. In spite of its apparently erratic flight characteristics, it succeeded in exhibiting an encouraging amount of stability, but the results obtained were not striking enough to warrant continuing the project. 1 year after the de Beaufezat machine had been abandoned, Emil Berliner was attempting to get this faltering craft into the air at College Park, Maryland. This was his 3rd and most nearly successful model. The photographic evidence at hand would hardly support the popular belief that a 3rd attempt is infallible. In Italy, Dascagno built this not ungraceful craft in 1930. Its record ceiling was 59 feet, distance 3,500 feet. With varying degrees of success, these and numerous other weird craft rose and fell in the headlines of aviation, each contributing something to this pioneer principle of mechanical flight. Two seemingly unsurmountable difficulties, proper control in the air and the price paid in weight and power necessary for direct ascent, appeared to have permanently grounded the helicopter for all practical purposes. Meanwhile, the fixed-wing airplane was making great progress in the conquest of the air. As military and civil demands for speed and carrying ability were met and surpassed, it became evident at last that aviation was on the beam. The way was clear for the tremendous development which has followed. But with the fixed-wing principle, speed in the air means speed in landing and taking off. For sustaining altitude, speed must be maintained in crossing high mountains in bad visibility. With improved machines and the development of flying technique, accident rates were reduced encouragingly in proportion to the number of miles flown. But the fixed-wing airplane will always have certain limitations. A pilot will always have to be a more or less highly trained engineer. Literally thousands of square miles will have to be tied up in airports. Worst of all, when an accident does occur, the loss of life and material is too often total. Because of these facts, and in spite of continual discouragements, the direct lift principle of flight has persisted. It has not only persisted, but in light of recent developments, it is reasonable to believe that it may eventually play as important a role as its fixed-wing predecessor. Had anyone suggested, during this early period of development, the possibility of the Da Vinci principle of direct lift flight ever being realized, its pioneer inventor might well have been quietly amused. But for the past 35 years, aeronautical engineers have known that it was possible to lift a flying machine into the air by means of a propeller rotating in a horizontal plane. However, as recently as 1932, the world's record for helicopter-free flight contained such decidedly impractical figures as distance, 1 kilometer, duration, about 10 minutes, altitude, 18 meters. In that same year, Professor Heinrich Facke of the famed Facke-Wulf aeronautical firm began work on a helicopter for the German government. His success was such that in the spring of 1938, his craft astonished the aeronautical world by making an exhibition flight inside the Deutschlandhalle in Berlin, with Fräulein Hanna Rösch at the controls. This ship, of course, broke all existing helicopter records by a considerable margin. In fact, it has gone into the records as the first successful ship of its type. One of the greatest barriers in helicopter design has been torque reaction caused by the large rotor. This unusual tendency of the fuselage to rotate in the opposite direction to the rotor was arrested in the FW-61 by the employment of twin rotors placed side by side and turning in opposite directions. At the time when the FW-61 was establishing its success, practical comparison of its speed and lift were made with that of the autogyro. The various designers of the now successful helicopter must pay a tribute to the late Signor de la Cierva, who constructed and flew the first successful autogyro in 1925. The Cornu helicopter had succeeded in lifting itself a few feet above the ground as early as the year 1909, but no material progress was accomplished in the helicopter field until after the considerable amount of enthusiasm for autogyros had come and gone, bequeathing the helicopter much information of value. Somewhat similar in appearance, the principal difference between the autogyro and the helicopter is that the rotor of an autogyro is not power-driven. While the autogyro obtains its lift from its rotor, the rotor serves only as a wing would serve a conventional aircraft. Its rotation is auto-rotation and is caused by the movement of the ship through the air. The autogyro achieves its motive power from a conventional engine and propeller. Its advantage over the fixed-wing craft may also be considered its kinship to the helicopter. That is, the rotation of its blades makes it capable of sustained flight at low speed, approximately 30 miles per hour. Extensive tests of the autogyro proved it to be at best a tricky ship to fly. It has, however, formed an interesting step between the now highly perfected fixed-wing airplane and the direct-lift helicopter. A few years ago, the U.S. Army Air Forces performed extensive tests on the autogyro, but the number of ships in the service has never exceeded 10. At the conclusion of these tests, The development of the helicopter had progressed so far that it was believed to have every advantage of the autogyro, plus many more of its own. In short, while the helicopter can hover, the autogyro is compelled to fly over 30 miles per hour in order to sustain altitude. An autogyro landing requires a glide angle and leveling off, hence more ground space than the 20-foot platform on which a helicopter can come gently to rest. While the rotor-type aircraft was found to be less efficient in power required than the fixed-wing aircraft, the compensating advantages of the helicopter were writing an important chapter in the long history of its evolution. Military secrecy has forbidden us any further knowledge of what, if any, progress the Germans have made with the FW-61 type of craft since the opening of the war. But developments in this country have centered principally around this very convincing Sikorsky model, which our Army has designated XR-4. This ship is unique in its single lifting rotor. Its directional control and torque reaction are very simply accounted for by the single controlled pitch small rotor at its tail. In a fixed-wing airplane, the wing is a shape designed to lift and sustain the entire mechanism in the air. The wing can do this only when a considerable amount of air flows across it. In use, the practical arrangement is to move the wing through the air. Thus, the wing speed is the speed of the whole ship, and the speed of support can never be zero. Actually, the rotor blades in a helicopter may be considered as airfoils or wings. By revolving the rotor, its series of wings acquire a speed of approximately 350 miles per hour at their tips, and so deliver the required lift, while the forward speed of the ship is still zero. In case of engine failure, auto-rotation and freewheeling of the main rotor of any helicopter are, of course, essential features. If these were not present, the machine would fall like a stone when the engine stopped. As a helicopter glides to Earth, it assumes the characteristics of an autogyro and may be landed accordingly. As the glide path is inclined, that is to say, as soon as the machine moves forward in its descent, the rate of descent in the glide is reduced. Under these circumstances, its reactions are similar to those of any slow-flying fixed-wing aircraft. A number of dead engine landings were deliberately and successfully executed by the XR-4 during its recent flight test. Lateral and longitudinal control are obtained in this ship by adjusting the pitch of the main rotor blades. It may be increased or decreased by the pilot at any desired point in their rotation, with a compensating but opposite variation of pitch at 180 degrees. As the lift of a helicopter is not dependent on forward motion, and as motion in any direction is affected by the main rotor, an adjustment of the blades by the pilot will tilt the ship sideways, forward, or in any direction, and so it will proceed in that manner, climbing, descending, or in level flight. As this control is actuated by the stick, and the pitch control of the small vertical air screw in the rear is operated by rudder pedals, the controls of this ship are not unlike those of a conventional fixed-wing aircraft, except that they are quite sensitive, and the tendency is to over-control. Throttle operation has been simplified in that climb and descent are obtained by simultaneously increasing or decreasing the pitch of the main rotor blades, together with the use of the throttle. Since an increase of rotor pitch requires more power to maintain the rotor at whatever RPM is desired, there is a synchronizing mechanism that opens the throttle as the pitch is increased, and thus maintains nearly constant engine and rotor RPM despite pitch changes. While at this time the XR-4 stands unrivaled in successful performance in the helicopter field, the Platt-LePage Aircraft Corporation at Edison, Pennsylvania, has been working under an Army Air Forces contract on a helicopter of their own design. This craft, with its twin rotors, bears a resemblance to the Focke-Wulf model. While its military designation is XR-1, its development has been less progressive than the XR-4. It has, however, been flying with an encouraging amount of success since May 1941. Manufacturing names such as Kellett, Nash Kelvinator, and others are also becoming important figures in the Army Air Force's helicopter program. competent authority believes that present knowledge is adequate to design and construct a successful helicopter of approximately 6,000 pounds gross weight, of which a reasonable percentage should be useful load. Though high speed is not of first importance, it should exceed 100 miles per hour. Range and endurance are predicted to be such that it should make an extremely useful instrument in combating submarine warfare. A series of tests have been conducted by the Army in order to determine the ability of this new type craft to operate from a small landing deck, which may be constructed on any seagoing vessel. As the weakest link in a chain determines its strength, so the slowest ship determines the speed of a convoy. Delay in assembling the varied units for a mass voyage, harbor congestion on arrival, and the employment of a naval escort are expensive items. In fact, so much is the convoy system a factor of cost and delay in the prosecution of an overseas military operation that any weapon which will permit greater freedom of action for cargo vessels will be of extreme value to our armed forces. It is believed that when a sufficient number of helicopters are available, ships of any size or speed equipped with small landing platforms may enjoy the individual and independent protection which the helicopter bids fair to offer against the undersea enemy of wartime shipping. The more comprehensive of two deep-sea tests which have been conducted with helicopters operating from merchant vessels was made in July 1943. The findings of this voyage were encouraging to the point that it is believed that a helicopter can be operated from a deck of this sort in weather bad enough to prevent the launching of fixed-wing ships from an aircraft carrier. Military and domestic prospects for the uses to which a helicopter may be put are unlimited. Equipped with low-pressure floats, there are perhaps no more than two types of surface on which a helicopter cannot land and take off: dense forest and heavy sea. With the aid of a rope ladder and the helicopter's particular ability to control its position so precisely in space, even these circumstances should not be exceptions to its performance of many military missions hitherto impossible or extremely dangerous because of the limitations of high-speed aircraft. Because forward speed can be reduced to zero, zero visibility is practically the only condition which will ground the helicopter. A sharp-eyed helicopter pilot can literally feel his way through the air by flying around trees and over large obstacles. Colonel H.F. Gregory, who's been in charge of the Army's rotary wing aircraft program since 1936, believes that since the helicopter needs no prepared landing field, it may provide excellent liaison and cooperation with ground forces. Artillery fire may be coached by direct line telephone communication. For behind-the-line missions at night, this airplane should be a real threat. With no propeller and a muffled exhaust, it can operate in almost complete silence. It can transport personnel and critical material to inaccessible locations, rapidly evacuate wounded men near the front, and unreel communication wires behind advancing troops over rugged terrain. Having no wings, the helicopter is less likely to be detected in flight than a conventional slow-flying airplane. Hovering stationary in the air, it will blend deceptively with the ground pattern below when properly camouflaged. In civil life also, this versatile vehicle will, without doubt, close many a link in the chain of practical aircraft operation. As with most post-war developments held out to the panting public, there will surely be a considerable interval of time before there is a helicopter on every roof and the two-helicopter family makes its appearance. But there's no question that the superior control and maneuverability of the helicopter will elevate it to a major position in advancement of transportation facilities. These scenes show stages of one of the first demonstrations of the helicopter to the American public. Another example of manipulative control is staged by the VS-300, the first of the XR-4 type helicopters, by picking up a small ring on a nose extension while in flight. The ring is transported across the area and delivered to a spectator standing by. This exhibition took place on delivery of this pioneer aircraft to the Ford Aeronautical Museum in Detroit. By way of diversion, here's a helicopter's eye view of a helicopter taking off from the deck of a cargo ship. The normal oscillation of the helicopter is considerably exaggerated by the lens of the camera. Two of the rotary ships are operating from this vessel in an experimental flight. Note the action is seen from one helicopter hovering in the air while the second aircraft leaves the deck. As it sweeps out over the briny sea, the helicopter bearing the camera approaches the deck and lands. We need not further enumerate the probable uses to which this fourth dimension of flight may be applied. We can, however, pause to marvel at the fact that, simple as its principle may now seem, it was conceived 400 years ago, and so must be accorded an unusually long period of legend among other principles of science. After all these years, it's good to know that at last the anxious mother's admonition to her pilot son, namely to fly low and fly slowly, may now be obeyed.
You know who I am. I'm Orville Wright, and I've come here to talk to you about, well, let me begin this way. I had this little incident recently, a close call. I was making my rounds of Army airfields, checking up on safety the way I do. I arrived at my destination and started my approach. It was a pleasant day, calm and pretty quiet. And then, all of a sudden, ouch! I wasn't badly hurt, but where had that turbulence come from? Hardly any wind, and there weren't any aircraft or helicopters flying around or even turning up. The only activity anywhere around was way across the field. But how could that Chinook have caused the turbulence? I hadn't been anywhere near his downwash, and everybody knows helicopters don't kick up any wake turbulence. Or do they? I was telling about what happened to me at the club that night, and it was clear that other pilots thought the same way I did. There's no wake turbulence from a helicopter. I asked his opinion, and I got answers like these.
Wake turbulence? Not from a helicopter.
Nah, it must have been a control system malfunction.
Downwash, yeah. Wake turbulence? No such thing.
Of course not.
No way.
But then I was right back where I started. If it wasn't wake turbulence, what was it? Well, I figured I'd try a little experiment. I waited for a helicopter to take off. Avoiding the downwash area directly below, I cut across behind it and slightly below. Whew, I almost didn't recover. I was a fool for trying it so close to the ground. but I had to know. So I went out and tried again at altitude. I took up formation position on a Huey, directly behind him. No problem. Then I tried holding the position, but dropping down a little, just a few feet. And wow, I got pushed down by turbulence that wasn't supposed to be there. I figured to give it one more try. This time, I took up formation position slightly below to see what would happen if I moved a little to the side. It had been a hard and tiring and scary experiment, and I decided it was snooze time. I started to doze off, thinking about what it had all meant. And suddenly, I remembered something. A movie I had once seen. Before I knew it, I dropped off to sleep. The movie came back to me in my dreams. It showed a model of a light aircraft in a smoke tunnel. You could actually see how the wing vortexes formed. Then it showed the real thing, wing vortexes from a jet transport. The smoke shows plain as day how the vortexes roll up on the outside and down in the center. It was already night by the time I woke up, but that dream had given me an idea. Find a smoke tower, have a helicopter fly past it, and see what happens. Simple.
Good idea. But we can't do it for you.
I've got no budget for a project like that.
I can't help, but let me know how it turns out, okay?
Sounds great, but who's going to build the smoke towers?
I did a lot of asking around and got a lot of turndowns. But if you stick with a good idea long enough, you almost always find a way. Take it from a wise old owl. Turned out the FAA had just what I needed at the research outfit in Atlantic City. I made all the arrangements and flew in for the test. The next day, everything was ready at last, and I thought, here it comes, the big moment when I'll get the proof. Nothing. It doesn't... Wait a minute. Look at that. Vortexes. 2 of them plain as day. It does. It really does. A helicopter does generate vortex turbulence just like a fixed-wing aircraft.
Now you know, Orville. There is vortex turbulence from a helicopter.
Who said that? Who are you?
Me? Why, I'm your friendly off-screen narrator. You know, the voice you always hear in training films.
Where are you? I can't see you.
Of course not. You never see me. I'm just a voice.
But what are you doing in my movie?
I've come to tell you some things about rotor vortexes. And I'll start with what you can see right here. Notice that there are 2 vortexes, one from each side of the rotor disc. They both roll inward and down in the center.
So that's why I was pushed down once and up another time.
Right. Now, when a helicopter is at a hover under no wind conditions, the turbulence, of course, goes straight down. At a slow forward speed, it begins trailing behind slightly. Faster, and it's going as much behind as down. Up around cruise speed, the turbulence wake is like a tail behind the aircraft, drifting down slowly to lower altitude. This tail can be quite long, as much as a couple of miles behind the helicopter. How large and severe the wake is depends more or less on the size of the helicopter and how much load it's carrying. When a helicopter is flying near the ground, the vortexes descend as usual until ground effect takes over. Then they start traveling along the ground at about 5 knots. But consider how the wind can affect this. With a crosswind of 5 knots, one vortex travels away twice as fast. The other remains at the same spot and may linger for several minutes. But the most important point of all is this.
The wake turbulence from a helicopter may be as intense as that from a heavy, high-performance fixed-wing aircraft.
As bad as that? Who would have thought it?
So then the question is, what are the safety guidelines a helicopter pilot should follow to avoid wake turbulence accidents? The most dangerous situation is close formation flying. You're okay so long as you stay at or above the level of the aircraft ahead of you. Do not let yourself descend below this altitude. That's where the turbulence is. Around an airport, you're operating near the ground and in proximity with other aircraft. You need to keep the turbulence hazard in mind all the time. If you're following another aircraft on approach, fixed wing or helicopter, remember that his turbulence is behind and below. Avoid it by following the same approach path or a steeper one. Be alert to how the winds can carry turbulence across the field to where you are, or hold it stationary at one spot on the field.
From away across the field? So that Chinook really could have been the cause of my problem.
Sure could have. It was generating a lot of wake turbulence. The wind could have carried it right across the field.
I'm convinced there really is vortex turbulence from a helicopter. It's always there, and it can be violent. Who would deny it? I'm convinced. How about you?
That was just one of more than 300,000 practice power-off landings that'll be executed by Army pilots this year. Well, that one pilot, it was another chance to rehearse, under completely controlled conditions, emergency procedures that might save his life, his crew, and his aircraft, if he should ever lose his engine while in flight. I'm Lieutenant Colonel Bob Evans of USAVES, the United States Army Agency for Aviation Safety. Now, as pilots, we all know that there is a certain amount of risk involved in any power-off landing. But we can reduce that risk if all of us, pilots, command, and staff, know what we're doing. Department of Army policy says we'll conduct practice power-off landings and also lay out standard conditions and procedures that will be observed. So for the next few minutes, we're going to review not only what happens during auto rotation, but also the parameters of the training environment established by policy that must be satisfied before practice power-up landing can begin. The whole idea is to get us up to speed to handle an emergency that we hope will never happen, and do it safely. It's important to have a good understanding of what's happening physically during auto rotation, because these factors underlie everything that's required for maximum safety procedurally. Let's look at the situation in normal, straight, and level flight. Rotor motion generates a downflow through the main rotor disc. Lift overcomes the force of gravity, or weight. A forward component of rotor thrust provides a force to overcome helicopter drag. All forces are balanced, and the engine is producing the torque to maintain a constant rotor RPM. But what happens if now the engine fails? Engine power is no longer available to maintain rotor RPM. Downflow through the rotor decreases to the point it is replaced by an upflow due to the aircraft's descent. Looked at in another way, as a result of the engine failure, lift and thrust start to decrease. In addition to this, another factor is aggravating the situation. The radical change in relative wind produces a high angle of attack, and the resulting high drag slows the rotor, threatening to stall the blades unless corrective action is taken. The danger is that without immediate positive pilot action to change the angle of attack, rotor RPM will decay rapidly due to profile and induced drag. And because rotor lift varies as the square of the RPM, lift capability will be lost at a substantially higher rate. If this continues too long, rate of descent may exceed auto-rotation capabilities for recovery. For example, a 10% reduction in RPM leads to a 20% reduction in rotor lift, a 1-to-2 ratio. For this reason, it is crucial to take all necessary steps as quickly as possible upon engine loss to ensure that rotor RPM is maintained. The obvious pilot action is an immediate down collective that promptly reduces pitch and angle of attack, and then to establish the required velocity of flow through the rotor that will ensure maintenance of rotor RPM. This can be achieved by descending vertically, but the rate of descent must be very high, in the several thousands of feet per minute, and obviously enough altitude must be available for this purpose. On the other hand, forward motion can be made to contribute a substantial share of the flow at a much reduced rate of descent. At zero or low air speeds, you can expect high rates of descent. The rate declines to some minimum point with an increase in airspeed, a flight condition you can choose by adjusting aircraft attitude in auto-rotation. In many cases, minimum rate of descent is the preferred condition. By changing attitude to increase airspeed, rate of descent again climbs until a maximum range condition is achieved. Increases in airspeeds beyond this point are no longer optimum and may even be dangerous due to progressive loss of lift. The standard procedures governing practice power-off landings in the Army are designed to produce a rate of descent that is a compromise between minimum descent and maximum range points. This also provides generous options for you to exercise in emergencies, allowing you to select any airspeed in the included spectrum for landing spot selection purposes without risking a hard landing. The allowable options translate into distance over the ground that, depending upon entry altitude, can be measured in the tens to hundreds of feet. If altitude remains the same, risk of hard landing, serious damage to the aircraft, personnel injury, or even death increases with either a decrease or increase in airspeed. Trying to stretch a glide by increasing airspeed beyond the maximum range rate of descent can lead to disaster, just as surely as decreasing airspeed below the minimum rate of descent. Looking at your options from overhead, range over the ground available to you from the initial entry point decreases if a turning maneuver is involved, due to the higher rate of descent that results from increased aircraft G-loading, even while RPM is maintained. Again, some degree of choice between minimum rate of descent and maximum range is available. But attempting airspeeds and rates of descent above and below the optimum band again can lead to serious consequences. All right, those are some of the concepts that apply to auto-rotation. But in the execution of the power-off landing, there are many additional factors involved. So let's consider it in more detail. The landing maneuver must be conducted in phases, each of which has a specific purpose related to controlling rate of descent or airspeed, or both. The line of flight from entry to touchdown is therefore rarely a straight line, except at descent angles close to vertical where forward ground speeds are low. Achieving proper flight conditions that will set up auto-rotation is of critical importance at entry. The objective is not only to down collective to reduce drag on the rotor, but also to counter loss of engine torque by adding right pedal, and then to select an attitude that will produce the proper airspeed and thereby the proper rotor RPM. This will place RPM in mid-green. You might call the initial part of power-off landing the steady-state phase. This serves two main purposes. You adjust the controls to maintain rotor RPM and consequently preserve a suitable degree of lift so that descent to a lower altitude can be achieved safely, and also to conserve the kinetic energy available in the rotating mass of the rotor for application during later phases of the maneuver. At about 100 feet above ground level, a new phase begins, deceleration. The objective here is to decelerate forward motion and increase rotor inertia and RPM. Deceleration involves a substantial change in attitude, placing the rotor nearly normal to the flow into the rotor. As it is exposed to the full flow of the airstream, the effect is to accelerate the rotor. But this increase in RPM is at the expense of airspeed, a deliberate trade-off, for during deceleration, the rotor is also building up both lift and kinetic energy due to that increased RPM. And both of these must be present if the next phase, at about 10 to 15 feet, is to succeed. During the entire auto-rotation to this point, collective has been pulled down. But now, an initial pitch pull puts a portion of that increased lift to work. During the initial pitch pull phase, that rotor energy that was built up is drawn on to sharply reduce rate of descent, and this affects both attitude and airspeed. By continuing to pull collective, you expend that high kinetic energy level built up in the rotor during deceleration, and which forces the rotor to continue its rotation during the landing phase, even though airspeed due to forward motion is lacking. The amount of kinetic energy stored in the rotor system is related to its mass and the effects of inertia. Low mass, low inertia rotors give up their energy quite rapidly. High mass, high inertia rotors persist in their rotation for longer periods of time. The effect is to cushion the landing, using the available lift to control descent, touchdown, and to hold the aircraft weight off of the landing gear during runout, if any. Only after aircraft motion is stopped do you down the collective fully to conclude the landing. That was a good standard practice auto-rotation. Each phase was carried out just about right on the mark. Now be advised that the penalty for failing to observe the successive requirements for each phase of a power-off landing can be pretty drastic. You can bend or ball up an aircraft without too much trouble. Test pilots have placed themselves at considerable risk in engineering test flights to locate the auto-rotative limits of each helicopter in the Army inventory. Sometimes the only way to find out where the limit is to step over it, like this pilot did. Fortunately, this time he walked away from it. Operating in the caution or danger areas of the high-velocity diagram, in this case low airspeed and insufficient altitude for auto-rotative recovery, can lead to hard landings. There's no denying the potential risks in power-off landings. But aviation safety organizations such as USAVES, together with various aviation center departments, have helped to define the operational and procedural constraints that can lead to the execution of practice power-off landings with reasonable safety. It's these constraints that underlie Department of the Army policy with respect to helicopter power-off landings. The controlling idea is that power-off landing is strictly an emergency procedure. It should never be indulged in just for kicks or casually in uncontrolled circumstances. Accordingly, Army policy requires us to conform to specified criteria before we enter flight training for power-off landings. And it also requires that this training be conducted according to standard procedures that have safeguards structured into them. Army policy says that practice touchdown auto-rotations are to be conducted only during formal instruction at the Aviation Center, during rotary wing transition flight training courses approved by appropriate authority, during standardization evaluation flights, and when deemed necessary by the appropriate commander. Policy clearly requires that practice touchdown auto-rotations are to be controlled by the local standardization board as an organized and closely supervised program. Survivability during what is training for an emergency goes up in direct proportion to to the extent which those policy criteria are applied. Afternoon.
There's little doubt that for the instructor or standardization pilot, practice touchdown auto rotations can cause pressure. For this reason, Army policy says that consecutive one-hour auto rotation instruction periods should not be scheduled in any one day. Further, no more than 6 practice touchdown auto rotations per instructor, pilot, or student are to be performed during any one instructional period.
Policy also requires that training be conducted at a location that provides for a crash truck with crew standing by, air-ground communications, and a means for opening and closing the practice area. For night practice, specific training locations must be designated and equipped, and all minimum criteria must be observed.
Policy also states that practice touchdown auto rotations may be carried out only in dual control equipped aircraft, with a qualified instructor pilot at one set of controls who is current and proficient in practice touchdown auto rotations in the mission, design, and series aircraft being flown. Only the minimum required flight crew is to be on board the aircraft during practice touchdown auto rotation. Inasmuch as each aircraft has its own auto rotation characteristics, all entry speeds and altitudes during the maneuver are to be as specified in the flight training publication for the aircraft that is being flown. The flight parameters used in these publications have been selected to present the student pilot with a set of conditions which, if followed, will offer maximum potential for safe execution of the auto rotation maneuver under the monitoring and control of the instructor pilot. Policy expressly forbids unanticipated surprise practice touchdown auto rotation maneuvers, so the student can concentrate on acquiring the necessary knowledge and skills for this vital emergency procedure, free of that particular pressure. The standard practice touchdown auto rotation then starts from an altitude of about 700 feet above ground level, or as directed.
Okay, wind up on final.
Collective pull down, throttle to flight idle, cyclic and pedals adjusted for coordinated flight. The steady state phase. Minimum descent airspeed. Maintain steadily, normally, without variation. Maintaining constant ground track. RPM holding steady. Approaching the next phase. The deceleration phase. Nose up slightly. Rotor nearing normal to the flow. RPM increasing, but held below 339 RPM by small collective adjustments. Airspeed decreasing in the expected trade-off of RPM for airspeed, expending rotor inertia for lift. Cushioning the descent to the ground with very little forward airspeed.
You've got all those points straightened out now that we've been talking about, especially that bit about reducing the collective to break the ground run.
The problem in doing that, of course, would be that the rotors might flex and cause aircraft damage.
The whole idea is to use collective to keep the aircraft light on the skids until run-out is completed to protect the landing gear. Elements of the standard touchdown auto rotation we've just seen are applicable also to field maneuvers, starting from different initial conditions, at low level, say.
So long as the highest obstacle is cleared by 50 feet, Army policy says the low-level touchdown auto-rotation can be performed at designated training locations, provided approach zones are sufficiently clear of obstructions to permit visual contact with the point of intended landing from auto-rotation entry to termination. That entry speeds and altitudes are as specified in flight publications for the aircraft being flown. That auto-rotations will be straight in, maintaining a constant ground track, and that speed reduction climbs or pop-ups will not be performed. As a practical matter, entry to auto-rotation may occur almost simultaneously with the deceleration phase, if entry altitude is near 100 feet AGL. And from then on, the maneuver is identical with the standard touchdown auto-rotation from higher altitudes. A standard touchdown auto-rotation with a turn differs mainly in the initial conditions. And as pilots, you'll need to pay some attention to what's happening to the aircraft during the turns that precede entry into auto-rotation. We're watching a maneuver that includes a 180-degree turn, but you're not limited to this provided other requirements are met. That you be straight in not less than 200 feet AGL, for example. If you'll remember, a while back we said that even if RPM is maintained, you'll experience a higher rate of descent during a turn due to increased G-loading. Because of this effect, you'll have to initiate the maneuver at sufficient altitude and be sure to maintain coordinated flight to be in a steady state condition by that 200-foot AGL mark. Auto-rotation then follows the pattern we've already described. Incidentally, while the flight training guides and other publications may call for minimum ground runs as the preferred termination, you shouldn't construe this as requiring precision touchdown or zero ground run auto-rotations. The policy with respect to forced landing exercises is straightforward. The Army encourages you to practice these maneuvers, provided they are conducted only to an approved training area. But descent must be terminated and power recovery executed at no less than 200 feet above the highest obstacle. Practice hovering auto-rotations are excluded from the minimum criteria we've been talking about. Except for instructor pilot training, policy says further that unanticipated surprise practice auto-rotations from hovering are to be eliminated.
The tactic here, remember, is to hold what you've got, because the situation could be critical. Rotor energy has not been built up. Increased pitch could slow the rotor down abruptly, causing immediate loss of lift and a hard touchdown. Hold the collective pitch setting, allowing RPM and lift to decrease slowly, cushioning the landing with remaining rotor energy as in the case of the standard auto-rotation by pulling collective slowly.
Of course, we've been talking about criteria and procedures in the training environment, and we haven't said a thing about what may be the most critical issue of all, surprise, and the crucial delay in pilot response it may cause. An engine can go at any time, under any operational condition, perhaps under something as straightforward as this mission involving 2 aircraft.
When you're in flight, survival may depend on split-second reaction and coordination. There won't be time for extended discussion about who's going to do what. All that has to be worked out in detail ahead of time, with a clear definition of which pilot will perform which duties, planned and accepted at the outset. Sort out individual responsibilities, pinpoint possible landing sites, do everything possible beforehand to cancel out the effects of surprise. Confusion in the cockpit can kill you, but not if you've thought the problem through and have trained yourself to deal with the unexpected, quickly, proficiently, effectively.
Having a pressure problem, someone had to take it down.
That instinctive reaction, automatic, precise. Collective pull down, adjust cyclic for 80 knot attitude, adjust right pedal to counter loss of torque. May have saved them, for the pilot is ready for auto-rotation entry if need be. number of lives and an expensive aircraft. Saved by prompt and knowledgeable response to an emergency that could have had disastrous consequences. Department of the Army policy accepts the conclusion that, as a minimum, current policies and procedures have been effective in Army aviation accident prevention efforts. My business is aviation safety, and a safe power-off landing like this one is the payoff for me. And it can be for you and everybody else who flies in Army aviation when your training for power-off landings takes the safe approach.
During a recent 2-year period, 33 Army personnel were killed by tail and main rotors while entering, leaving, or working around Army aircraft. It is of paramount importance that during your training, you learn, master, and at all times thereafter, follow the safe procedures for entering or leaving aircraft to protect yourselves from tail rotors and main rotors. The following rules must be observed for safe boarding of helicopters. First, be sure the helicopter has fully touched down. The pilot must be sure that the helicopter's rotor system is level. You must always use caution when approaching an aircraft, whether as a passenger, refueler, mechanic, or loader. You should approach a helicopter within range of the pilot's vision. That is, within an area 90 degrees right or left of the nose of the helicopter. Never go around the tail. Radio men must ensure the radio antenna they are carrying does not protrude upward in such a manner that it will come in contact with the rotor blades. Of course, if a fixed wing aircraft is involved, and for any reason you have to go around it, you must go by way of the tail to avoid the plane's propeller. You must always keep in visual contact with the aircraft you are approaching. With the OH-6A or the OH-58, you have a special problem. After being sure the pilot has fully touched down, approach this helicopter with even more caution, if that is possible, because of the unusually low rotor blades. A combination of low rotor speed and high gusty wind increases the hazard to personnel in the immediate vicinity of the aircraft. When leaving the aircraft, the same rules apply as on entering, and be certain that all loose items have been secured. The dangers here are apparent. In loading and unloading internal cargo, the same rules for personnel safety apply. Always be alert and keep low. It is a safe habit to get into and keep. It can save your life. In the case of the CH-47, the pilot must be sure that the helicopter rotor system is level and the aircraft is fully touched down before loading troops or internal cargo. When loading or unloading personnel and/or portable cargo, the loading ramp should be approached only from the right or left of the helicopter's tail within a 45-degree fan area on either side of the aircraft. This is to avoid the excessive exhaust temperatures directly behind the aircraft. Under normal conditions, the CH-54 tail and main rotor blades present no problems in coming in contact with personnel on the ground. But remember, it is a helicopter, and precautions must be taken. You must always look out for blowing objects caught up by the rotor wash. In addition to tail rotor and main rotor blade hazards, armed helicopters, such as this Cobra AH-1G, present additional dangers through their weapons systems, and they should be approached with extreme caution. When operating in rough terrain and/or combat situations, you must give close attention to the aircraft commander's instructions for departing or entering the helicopter. In extreme conditions of terrain, where the helicopter cannot fully set down, close coordination must be maintained between crew and passengers to avoid dangerously low rotor blades. Passengers must be instructed how to exit the aircraft on the upslope side of the helicopter, where the tail and main rotor blades are nearest the ground. The same precautions apply to any model of helicopter used in this kind of situation. When operating in an open terrain area, personnel must always be on guard for loose objects on the ground, which may be blown around by the rotor wash. Rotor wash effects increase in proportion to the size and weight of an aircraft. These helicopters are directed in the refueling area by ground personnel who should be dressed in proper work uniforms, wearing eye goggles and leather gloves, sleeves rolled down and buttoned, and leather boots. Dress in this manner protects personnel from flying debris and any fuel spilled during the refueling operation. When the aircraft has been parked in its proper refueling position, you wait before refueling to ensure that the aircraft rotor system is level and until you receive your go-ahead signal. The aircraft should be maintained at full operating RPM to facilitate aircraft clearing the area in case of fire in an adjoining fuel point. The crew chief gets out, opens co-pilot and pilot doors, slides armor shield to rear to make it easier for crew to escape in case of fire. Passengers must get off the aircraft and move to a safe area. All crew members will have their visors lowered. After assuring there are no open flames or smoking in the area, the crew chief with fire extinguisher in hand supervises the refueling operation. The refueler grounds the aircraft and attaches the nozzle grounding cable. The crew chief checks for proper grounding. The refueler removes the fuel cap, places the nozzle fully into the filler port, and begins refueling. Once the closed circuit system is attached to the aircraft, the refueling is automatic. In case of an emergency departure, the nozzle will disconnect. This is a design feature of the closed circuit system. This system may also be used to refuel manually. The crew chief must be in a position where he can see both the pilot and refueler, so he can signal between them. After reaching the desired fuel load, as indicated by a signal relay from the pilot by the crew chief, the refueler stops the fuel flow. He removes the nozzle, replaces the filler cap, disconnects the nozzle and aircraft grounding cables, and returns the nozzle to its rack. The crew chief returns the fire extinguisher and readies the aircraft for flight. The passengers are reloaded. These procedures may vary due to the configuration of the aircraft and type refueling system used. Personnel working around the OH-6A must use extreme caution due to its extremely low rotor blades. In addition to the low rotor blade danger, there is always a possibility of fuel feedback during manual refueling as the explosive fuel is flowing into the fuel tank. With the UH-1C and the UH-1M series aircraft, extreme caution must be taken in manual refueling due to the location of the refueling port. The same is true of the AH-1G Cobra. The fueling port is higher than normal and located near the engine air intake. If the nozzle slips out of the fueling port, or if a surge of fuel flow causes spillage during manual refueling, it could go into the engine, causing excessive acceleration, possibly damaging the engine and the driven components or start a fire. The closed-circuit system shown will eliminate all of these hazards. The closed-circuit system should be used on all aircraft when possible. The CH-47 helicopter, while big and high, has front rotor blades to watch out for. In a high wind condition, all blades are dangerous to personnel because they can flex down lower than normal. But the front blades are more dangerous as they are the lower of the two rotors. The flight engineer must be in a position to supervise refueling on both sides of the aircraft because there are fuel tanks on opposite sides of the helicopter. He must maintain communications with the pilot at all times. The CH-54's special problem is the location of its exhaust near the refueling port and the excessive heat it puts out. In this case, we shut the #1 engine down to avoid the excessive exhaust temperature on the refueling personnel and the open fuel port. This applies to both manual and pressure refueling. Prior to arrival of the aircraft, the sling loading hookup area should be cleared of all loose objects that might be thrown about by rotor wash. Only personnel involved in the operation should remain in the area. On arrival, the pilot in command will determine that the ground personnel are positioned and ready for the hookup. The signalman must maintain a position 30 to 50 meters in front of the load facing the aircraft, where he is in constant view of the pilot. When hovering toward and over the load for the hookup, the pilot follows the signalman's directions. While the helicopter is over the load, the aircraft crew and hookup crew must be constantly alert for possible engine failure. It cannot be overemphasized that due to the nature of the turbine engine, a power loss or engine failure may occur with no warning to either ground or air crew. Constant alertness is imperative. Engine failure. The pilot releases the load. The signalman turns away from the aircraft and dives to the ground. The hookup man dives and rolls as far to the right as possible. They cover their heads with their arms to protect themselves should the helicopter crash. The pilot executes an auto rotation to the left of the load. After a normal hookup, the hookup man will move to the right and forward. The signalman will direct the pilot as he lifts the load, checks for other aircraft in the area, and clears the pilot for takeoff. The same general safety rules apply with a CH-47, except that no signalman is used. His duties are performed by the pilot and the flight engineer, who can effectively observe operations through the floor hatch of the aircraft. During hookup, static electricity on the cargo hook cannot be effectively dissipated from within the aircraft. Electric shock can be avoided by grasping the rigging donut with gloved hands. With the CH-54, safety rules are similar. No signalman is used, as his duties are performed by the pilot and flight engineer. They can effectively observe operations from their positions in the aircraft. Static electricity is not normally a problem. The loading scenes just shown do not cover all types of sling operations. Other loads, such as ammunition, heavy weapons, and vehicles, involve safety procedures peculiar to these types of loads. Standard procedures for handling various loads and aircraft should be reviewed frequently and followed by all personnel concerned. This will promote greater safety during this hazardous operation. When moving and parking aircraft on an airfield, all movements will be coordinated and controlled through the aircraft traffic controllers located in the airfield tower. Only designated hovering lanes and parking spots should be used. Hovering lanes and parking spots are indicated by painted stripes, airfield lights for night work, or other indicators. Their usage varies with the airfields, and a complete explanation of each airfield can be found in the operations office. Aircraft crews will familiarize themselves with the correct procedures of the airfields they will be utilizing. When moving and parking on an airfield, the aircraft crews should use caution to avoid maintenance vehicles, maintenance personnel, other aircraft, and miscellaneous personnel and equipment which might be located on or near the hovering lanes and parking areas. Personnel on the ground should avoid positioning themselves or any equipment in any location that would obstruct aircraft movement. Any loose equipment should be secured whenever rotor blades are turning in the area. Aircraft crews observing any safety hazards on an airfield should avoid them and make a report immediately to the ground controller. Landings at other than established airfields, such as rough or unprepared terrain, will involve ground movement and parking procedures which are different from the normal ones. The pilot in command is responsible for safely moving and parking his aircraft. If no ground handling personnel are available at rugged sites, movement is accomplished by full utilization of his crew to avoid any obstacles or personnel in his path on all sides. Because the CH-47 is so large and has limited visibility, ground handling personnel are required to safely move the aircraft when operating in a restricted area. Ground handling personnel should be utilized in conjunction with the crew on board to safely move the aircraft. If ground handling personnel are not available, a crew member must be dismounted and used instead. To avoid confusion between ground personnel and the aircraft crew, ground personnel must be thoroughly familiar with and use only the standard hand and arm signals and equipment described in Field Manual 21-60. They must be familiar with the requirements and procedures for both day and night operations for each type of aircraft. Ground guidance personnel must be fully dressed in proper work uniforms, goggles and ear protection, gloves, and a fully serviceable uniform. The position of the signalman when directing utility aircraft is in front of it, where he can best be seen by the pilot. A special caution when directing armed helicopters, such as the AH-1G Cobra. The signalman must not position himself directly in front of the aircraft at any time. Stay to either side of the front. With the CH-47, caution should be used not only to avoid direct contacts between the rotor blades and other objects, but to prevent damage resulting from rotor wash and flying debris. Maintain as much distance as possible between the aircraft and any possible item which may be damaged. All aircraft crews must be dressed in complete flight uniforms to include flight helmet, Nomex gloves, the Nomex flight suit, and leather boots. At all times, helicopter engines are being started or are running. Helmet face shields must be down during refueling operations. SPH-4 helmets should be worn by crew members for ear protection. Ground personnel must wear protective earmuffs. Uniforms must be fully serviceable, that is, no holes, no rips or tears. During cold weather operations, additional clothing may be desirable, but movement or vision must not be restricted. Maintenance personnel must be fully dressed in proper work uniforms. They should wear Nomex suits if available. When near a helicopter, remember to remain well clear of the tail and main rotor blades. On some helicopters, the main rotor blades are low and extra caution is necessary, especially during high wind situations. Caution around turning rotor blades cannot be overemphasized. Aircraft require proper grounding during refueling operations. Avoid fuel overflow, feedback, or sloshing out. Fire is a great hazard. Hookup teams, properly positioned and well briefed on procedures, minimize dangers. Ground handling and aircraft crews must be thoroughly familiar with and use only standard hand and arm signals. Aircraft crews must be properly dressed during all aircraft operations. Properly dressed ground crews minimize exposure to flying debris. Every aircraft has its own inherent dangerous characteristics. Your life depends on learning and following standard safety procedures. The time to start is now.
Helicopters, the most versatile equipment to appear on the scene in recent years, are making possible new concepts in transportation for both military and civilian use. The helicopter has earned a place of importance in aviation because in small confined areas, it can take off or land vertically. It can move forward. It can move sideways in either direction. It can move backwards. And if the engine should fail in midair, it can make a safe emergency landing. Although the helicopter has only recently become a practical means of transportation, its idea has occupied man's thought for centuries. Leonardo da Vinci expressed his idea for a flying machine in the 15th century. Others followed da Vinci in dreaming of vertical flight for man. In 1783, a French scholar, Lannoy, and a French mechanic named Bienvenu demonstrated to the French Academy of Science a flying top made of feathers, sticks, and string, like this model you see here. It was the first heavier-than-air device ever to fly on its own power. Half a century later, an English schoolboy, George Cayley, heard about Lannoy's flying top. In 1843, he designed a four-rotor model helicopter, but having only heavy steam engines available for power, he never tried to build a full-size machine. In 1878, Enrico Forlanini of Italy built a model powered by a midget steam engine, which actually hovered at 40 feet for 20 seconds. The advent of the gasoline engine marked a turning point in the development of the helicopter. Inspired by the success of a pilotless machine built by Charles Renault, his student Louis Breguet built this helicopter in 1907. It carried him to an altitude of 5 feet. This flying octopus was built by Dr. Georges de Bautizat for the United States Army Air Service and test flown in 1922. It rose to a height of 5 feet and stayed aloft for 1 minute and 43 seconds, but was too complicated and proved impossible to control in flight. In that same period, the American Emil Berliner and his son Henry built 2 machines. This, his second, proved fairly successful. Experiments continued throughout the world, and in 1923 came a significant development. A Spanish inventor, Juan de la Cierva, developed the autogyro. It was a cross between a helicopter and an airplane. It had fixed wings and a standard propeller to raise it off the ground. A free-spinning rotor on top gave additional lift. He was able to cross the English Channel in this machine, and his principles of design were to lead to a successful, true helicopter. In 1934, the Frenchman Louis Breguet tried again. This time he achieved real stability and control. In fact, his machine is generally considered the first practical helicopter. In 1937, the German Heinrich Focke built this FW-61. It could hover, go straight up or down, and move forward or backward. It set new records for endurance, speed, distance, and altitude. Other inventors, of course, were hard at work developing different ideas in helicopter configuration. Here in America, Igor Sikorsky, who had been carrying on rotary wing experiments for years, made his first free flight with this VS-300 in 1940. Although the Army had already commissioned the Pratt-Lepage Company to build a helicopter, it followed Sikorsky's progress with keen interest. As a result of Sikorsky's success with the VS-300, that model was used as a prototype for the first helicopter designed for military use, the Sikorsky XH-4. From this basic design came Sikorsky's later models, the H-19.
then later the much larger and greatly improved H-34. Other designs by American inventors were being developed. In the late 1940s, 2 more models were accepted by the United States Army. One produced by Bell was the forerunner of this, H-13. The other was the H-23, manufactured by Hiller. Piasecki designed the H-25, a small, compact utility helicopter employing the principle of 2 rotors driven by a single engine. He also devised another tandem rotor machine, the H-21, known as the workhorse. Cayman built machines such as the HOK series, using 2 rotors mounted side by side and so synchronized that the revolving blades intermeshed. Even though these present helicopters are satisfactory, research continues to explore new fields. The search for a practical small helicopter has resulted in this experimental 2-place model powered by ram jets on the blade tips. In the 1-man class is this simple, compact version of the conventional helicopter. Developed by Hiller, it has the advantage of being collapsible and easily carried. A distinct departure is the flying platform, with its rotor blades mounted on a frame under the pilot. Directional control is accomplished by the pilot's body movements. Seeking engines with higher horsepower and more efficient operation, designers have turned to turbine engines. One, designed by Lycoming, is used in this Cayman HOK. Bell's latest utility helicopter, designed for the Army, the XH-40, also uses the Lycoming turbine engine. In reaching out for greater and greater capacity, Sikorsky uses 2 engines to drive 1 main rotor in the H-37. Although we have accomplished a great deal in the development of the helicopter, we have even more to accomplish in the future, and the task is not without its difficulties. Rotary wing was man's first idea of flight, but practical helicopters were not produced until long after fixed-wing craft filled the air. This was because helicopter pioneers had to solve so many additional problems. Consider some of the problems and the solutions which made rotary wing flight possible. Take a bird's-eye view of the 2 types, fixed-wing and rotary wing aircraft. There is a resemblance. Rotor blades are really wings. That's why helicopters are called rotary wing aircraft. So first let's see how a fixed-wing aircraft flies. Then go on to the helicopter. In flight, 2 basic forces must be overcome: weight and drag. The forces which overcome these 2 factors are lift and thrust in fixed-wing aircraft. Lift is obtained from the velocity of airflow over the airfoil or wing and is about equal to the square of the velocity. Thrust is obtained from the propeller, which drives the aircraft through the air. So the greater the thrust, the greater the velocity of the airflow, and the greater the lift. Another factor which affects lift is a change in the angle of attack of the wing, as shown here. The angle of attack is the angle formed between the chord line of the airfoil and the relative wind. Increasing the angle of attack up to the stalling point will increase lift within the limits of airfoil design. Now, any increase in the flow of air or in the angle of attack, or both, will increase lift. A conventional fixed-wing aircraft gets most of its lift from its wings. The helicopter gets enough velocity of airflow by rotating its blades at speeds up to 350 miles per hour while standing in one place. To increase the angle of attack, the pitch of the rotor blades themselves is changed. In all helicopter rotor blades, two types of pitch changes are possible. The first, called collective pitch, gives a change in the angle of attack which is constant and equal on all blades. By changing this collective pitch, the helicopter can make vertical movements up or down, or it can hover. The other type of pitch change is called cyclic pitch change. In it, the pitch or angle of attack of each separate blade is being constantly changed as it revolves. This means that during each revolution, there is a constantly changing increase and decrease of pitch put into each blade. One effect of this changing is to tilt the plane of the tip path in the direction of flight, causing the helicopter to move in the direction in which the rotor is tilted. One reason for cyclic pitch change is to overcome dissymmetry of lift. This term, dissymmetry of lift, simply means the difference in lift between the advancing blade and the retreating blade in the rotor system in forward flight. However, the cyclic pitch change tends to balance out this difference. By decreasing lift on the advancing blade and increasing lift on the retreating blade, the symmetrical lift is restored and the rotor system is balanced in flight. To fly forward, the rotor disc must be tipped forward. To do this, we introduce low pitch to the pilot's right. Following the laws of physics, the effect will take place 90 degrees later and will tend to tip the rotor disc directly to the front, where there is less lift. At the same time, rising pitch is applied at the pilot's left, and it takes place 90 degrees later directly behind. In actual operation, cyclic pitch is gradually changed throughout the rotation. But its effect is to tilt the rotor forward, making the helicopter move forward. This cyclic pitch change, applied independently to each blade in the rotor system, governs horizontal movement. Now there's another point to be considered in helicopter flight principles. The problem is that of torque. In most single-rotor helicopters, the blades turn counterclockwise. Under Newton's law of equal and opposite reactions, the force of the turning rotor tends to make the fuselage turn around the rotor axis in the opposite or clockwise direction. If there were no means of controlling torque, helicopter flight in any direction at all would be impossible. Torque, however, can be controlled by an anti-torque rotor mounted on the tail boom. By changing the pitch of these anti-torque rotor blades, the helicopter can be turned in any desired direction. In tandem rotor designs, torque is no problem. As the rotors turn in opposite directions, the torque of one cancels out the other. This is true if two rotors are mounted separately or if both are mounted on the same mast. So much for the principles of rotary wing flight. Now let's take a look inside the cockpit at the flight controls by which the helicopter is operated. Alongside the pilot is the collective pitch stick, which changes the collective pitch of the rotor blades and causes the helicopter to move up, down, or to hover. A motorcycle-type throttle is mounted on this stick. The cyclic control stick tilts the rotor and causes the helicopter to move forward, backwards, or sideways. These anti-torque pedals are coupled to the tail rotor. By varying the pitch of the rotor blades, the helicopter is turned to the left or right when hovering. With the development of the helicopter into a practical reality, new uses are being found for it every day by private industry, government agencies, and military services. For example, oil companies find that helicopters earn their pay in running preliminary surveys and in patrolling their pipelines. Even the farmer has found a use for the helicopter in crop dusting. The low and fairly slow-flying helicopter can put the spray where it is needed in a hurry. Inaccessible areas are opened up for on-the-spot news coverage by airborne television cameras. The Postal Department also is found to use for helicopters. It has become quite commonplace now to carry mail from a downtown post office to a nearby airport for direct transfer to a cross-country airliner. Traffic police use helicopters to patrol the highways and prevent dangerous traffic conditions from developing. Conservation officials find it useful in counting elk and other wild animals in game surveys. Game can be herded toward better feeding areas or have food delivered to them in bad winter weather. In time of civil emergencies such as flood, the helicopter is called upon to carry medical supplies and food to isolated victims or to evacuate them to places of safety. Today, the military services are among the more important users of helicopters. Commanders find they can get to advanced units quickly to keep themselves abreast of tactical situations. Official messages and personal mail delivered from headquarters to isolated units can speed up communications and strengthen troop morale. Telephone wire on speed reels can be laid over rough terrain in a matter of minutes, a job which otherwise would require hours of work by the usual ground team. March control is handled more efficiently when a helicopter is aloft to spot traffic delays and to find possible alternate routes. For artillery units firing at concealed targets, helicopters serve as mobile aerial platforms for the forward observer. Cargo transport craft can support military operations by delivering heavy equipment, such as artillery, or a quarter-ton truck, or even sections of a pontoon bridge. Combat troops isolated by difficult terrain conditions can receive quick delivery of ammunition, medical supplies, gasoline, or other needed equipment. During the Korean conflict, this machine gained respect from fighting men by its ability to evacuate wounded from battlefields under conditions in which other means of transportation were almost useless. However, this vehicle's greatest value to the Army lies in the fact that a commander can plan on going over as well as around an enemy. Knowing that troops and equipment can be delivered to virtually any point when needed, he can proceed with confidence. The helicopter, then, can well be considered a new weapon in the hands of the field commander. Through its versatility, it provides the commander with the ability to maneuver and gives him the shock action necessary to assure success on tomorrow's battlefield.